Okay, let's get started. So we are going to start a new topic today, but let me just make a few announcements before we start. This week is the week before spring break, right? Usually in this class we have a midterm. Midterm is always, not shouldn't say always, but for the large part we hold it after the week after spring break. So that's the same thing this time. It's going to be the Thursday after spring break. Okay, it was already announced on the very first day of class. The exam, both the midterm and the final exam dates and times have been on the course schedule page. That nothing has changed. Just announcing here that we still plan to have the midterm on the Thursday after. It's going to be an evening exam, okay, and it's going to be in a different room, not in this room. The room I will post on the schedule page and also send via email. It's going to be closed book, closed notes, so it's not an open book exam. And I cannot remember what all lectures are on the midterm, but I think it's at least through this week, which means today's class and one on Wednesday will be probably what is on the midterm. So the Monday after spring break, we will have a class, but that will not be on the midterm. Okay? So everything we do through this week is what I believe is going to be on the midterm. Okay? I will also hand out some a sample exam from the previous year, so you can see what it looks like. I'll also make some sample problems. I haven't given out a homework really, which we had planned, but somehow there's been a lot of assignments we've been giving out, and I have not given a homework, but I will give out a set of sample problems for more as practice for the exam, right? So that you have enough to study and prepare. Okay. All right. So let's get started. So today we are going to start a new topic, which I broadly refer to as classical problems in distributed systems. So we will look at these problems on the next several classes. And the way you want to think about it is when you design these large-scale systems of any sort that are distributed in nature, there are a common set of problems that arise over and over again, okay, across a large set of problems. So we abstracted those problems out, and we are going to study each problem and try to see how can you come up with approaches to address that problem. Okay? And then you can take those ideas and apply them to real problems. So we are going to talk about these more in the abstract, not in the case of, not by looking at specific systems, but just trying to see, okay, if you wanted to do synchronization, or you'll see the list of topics here, or leader election, mutual exclusion, which is really distributed locks, transactions. We will talk about consensus. There's a lot more beyond these that we are going to look at. And so we'll look at all of these in the next several classes. And then in the last third of the course, we will look at real systems, more case studies. We'll also see how some of these ideas apply there, as well as look at other design aspects of those systems. So that's really the context for what we are going to be talking about. So today, I'm going to talk about time ordering, clocks, clock synchronization, and something called logical clocks. Okay, and we'll continue that next time and then switch to leader election. Okay, so let's start with clock synchronization. I first will explain what is the problem that we are trying to solve, why is it relevant in distributed or even any computing system, and then try to figure out how we address it. Okay, so first thing is to realize that clocks and time is actually used in all kinds of computing systems. When you did your lab 1 evaluation, okay, you are supposed to measure latency. Okay, the way you measured latency was using timestamp. So you looked at how long a request took and you measured the time. Okay, so this implicitly assumes that the computing system that you're using has a clock. Okay, it keeps time. And then you can read the values from that clock, and those timestamps can be used for various kinds of analysis. In your case, you used it to figure out latency, but there are all kinds of uses of for actually using this timestamp. Okay, so essentially we assume that any computing system, and as thus far we are only talking about a single system, not a distributed system, has a clock in it. So technically what happens is there's a chip on your computing system that is basically a real-time clock chip. It keeps time, just as you have you have other things that tell you time. Your phone or your watch tells you time. The same thing is true of your computer. It has a chip that keeps time, and then that time actually you can read in using programs. Typically, that system clock is called a crystal-based clock. The chip is essentially crystal-based clock or quartz clocks, and they are pretty accurate. Okay, so they're essentially accurate to 1 part in a million, which means that every million ticks of that clock, it might lose one sort of tick in there. So I mean, they're reasonably accurate, but we will see what happens when these inaccuracies arise. Okay? So here's an example of what might happen if you have now not one but two computing systems and you're looking at time across two systems. Okay? So we'll assume that there is computer 1 that has its own clock, and this computer 2 that has its own clock. Okay? These clocks might not be exactly synchronized with one another, and if they're not synchronized, problems can occur. And here is an example of what might happen, and this basically is essentially talking about using make or doing simple builds of programs. Okay? So and first you need to understand how builds work. So typically a program such as make, okay, does what is called incremental builds. It only, when you type make, it will only compile files that have changed since the previous invocation. Okay? The way it's going to do this is it's going to take the timestamp on the binary that was created last time, and it will compare that to all the source files. And if any of the source files have changed since the binary was built, you will say some files have changed and those files are recompiled. You don't recompile everything. You only compile files that have changed. Okay? Now, it might so happen that if you have two machines that are being used for two different purposes, you have, let's say, a machine on which you write code, that's your development machine, and there's another machine where you build code, that's your build machine. It's a typical environment in any software engineering companies. That's how you do it. You write code on typically your desktop and things like that, but you build on some other servers. Okay, so you don't necessarily do local builds. But now these two machines have two different clocks. If the clocks are not synchronized, you might have a problem where, let's say, you make a file, edit to a file, and you save it. Okay? Now the file has changed, it gets a timestamp. Okay? Now if you're, let's say, when you now then try to build this file by invoking the build program or make on another machine, if that clock is off, it might actually believe that the file has not changed since the previous invocation. In particular, if the clock on the development machine is running way behind, your binary was, let's say, was built 10 minutes ago. Your clock is 15 minutes behind real time. And even though you change the file, okay, it's getting a timestamp 15 minutes in the past, not current time. So the build machine will believe the file has not changed because the binary looks newer than the modified file, and it will not build that file, and you will not see that binary actually reflecting your changes. Okay? This is a very simple example. That's what is actually shown here. Okay, but so your two machines, the clocks are off, and it's basically threw off a build program. Okay? But there are many such examples you can construct. Okay? What this is showing you is now the reason this problem arose is now the timestamps are being compared across two machines. Okay? There's a timestamp on the build machine that's assigned to the binary file, and there's a timestamp on the development machine that's assigned to the source file. You are comparing them to see in the make program whether to redo the compilation. Okay? But since the clocks on the two machines are not synchronized with one another, this causes problems. Okay? So this very simple example should tell you when we have a distributed system, okay, and you are using timestamps on many different machines, the clocks on these systems have to be synchronized. Otherwise, you cannot compare these timestamps. Okay? Because if the clocks are off, then you can't actually say what order some events occurred, because in this case, you are using timestamps to figure out when certain events occurred, whether the file changed after the binary was built or has not changed. Okay? So that's a very high-level motivation for synchronization. We'll get back to that in just 1 second, but let me start with a primer on how we tell time, right? So because we'll get back to some of these issues in today's class. So typically in the old days, you used the stars and the sun to tell time. Okay? Noon basically meant that you're basically the sun was right above, there's no shadow. That's basically the definition of solar noon. Okay? Now these days, of course, you don't use the sun to tell time. You have more accurate clocks. Yeah, your crystal-based clocks, which are the kinds of clocks we have on your wristwatch, there's quartz clocks, there are similar clocks on your machines. But the most accurate clocks are essentially what are called atomic clocks. Okay? So these are accurate to 1 part in 10 to the power 13, which means that they will lose a second every, I think, tens of thousands of years or something like that for a very long time. So they're very, very accurate. And that's what is the reference clock that is used to tell time. Okay? So what happens is many countries actually maintain their own atomic clock, and then they broadcast the time from this atomic clock. And if you want to synchronize any clock with the atomic clock in that country, you have to somehow tap into that broadcast and synchronize. Okay? Now, essentially, you can use satellites to broadcast that time. Actually, all cell networks also broadcast the time. So if your phone is connected to a cell tower, it's automatically synchronizing because the cell towers are broadcasting time that they're fetched from an atomic clock. So there are many, and there are shortwave radios that broadcast time. So there are many ways the time that is actually being computed by your atomic clock in any country are broadcast out, and then you can listen to them and synchronize. Okay. So that's basically how a lot of this works now. So your clocks are not going to be as accurate as an atomic clock. So every so often is going to be off, and you will have to resynchronize by changing the time. Okay, you don't do that on the phone because there's a program that's doing it for you, but it is actually synchronizing often. But if you had a mechanical clock of some sort, you would have to do this every time it loses some time. Okay, so this problem where the clock, an actual clock, drifts from real time is called clock drift. Okay, so the clock is drifting away from real time. Okay, and then we want to resynchronize this clock so that essentially the drift is brought back to something close to zero. Okay, that way, that clock will now again tell you time that's more accurate than what it was telling you before. Okay, so that's basically a primer on clocks. Now we'll see how to do clock synchronization. Okay, so there are dozens and dozens of clock synchronization algorithms that are out there. Okay, by and large, they will all follow one or two very simple ideas. Okay, so this slide here tells you the simplest idea behind clock synchronization, which is how frequently should you synchronize a clock with some sort of a master or an atomic clock. Okay? And the way you will decide this is we'll assume that any real clock, which is not an atomic clock, has some maximum drift rate rho. Okay? That's the maximum amount by which it is drifting from real time. Okay? The rho property is going to be determined by the type of clock it is. Right? So if you have a quartz clock, it may lose a second every few months. If it's the real atomic, not an atomic, a mechanical clock, it might lose a few minutes every week. Okay, so the drift parameter rho comes from the type of clock it is. Okay? And so different types, depending on how the clock was designed, there will be some drift parameter that the manufacturer of that clock will specify, saying this clock is accurate plus minus 1 minute every 1 month, or they might specify some number like that, and that is going to be a drift rate. Okay? So that is given to you. Saying when you buy a clock of any sort, it comes with some tolerant accuracy value, and so you know that drift rate. Okay? So what that means is essentially, if you look at this graph here, right? So your x-axis is real time. This is a time, atomic clock or actual time. The y-axis is the clock time. Right? If you had a perfect clock, every time real time advances by 1 second, clock time will also advance by 1 second. Okay? So in other words, you will essentially be following this line here, which has a slope of 1. Okay? Which basically means that if your clock is essentially, if it follows this curve, it's actually giving you perfect time, because every time time advances by any amount, the clock time will advance by the exact same amount. Okay? But as I said, actual clocks will not be perfect. They will have a drift parameter rho. So they will be either run faster than real time or slower than real time. Okay? If you're faster than real time, that essentially means that you are essentially advancing along this dotted line that's labeled fast clock. Okay? So here your slope is 1 plus rho. So you are essentially, every time advances by 1 second, the clock is taking by 1 plus rho seconds. Okay? And if you're slower than real time, you are going to have a slope less than 1. Okay? And the slope is going to be somewhere, in the worst case is 1 minus rho, but it will be somewhere in between. Okay? So what that means is this clock that you bought, okay, it will basically be within that window between the fast clock and the slow clock, depending on whether it's faster or slower. Those are the max bounds by which they can be off. Is that clear? Okay. So now we know how the clock is behaving. So now we basically want to see how to synchronize it. So what this also tells us is, if you are given any two clocks that are built with the same technology, the maximum value by which they can be off, okay, is 2 rho times delta t every delta t second. Because the worst case is one clock is essentially advancing at the slow rate, another clock is advancing at the fast rate, or drifting apart from each other. Okay? So every delta t seconds, these two clocks will essentially drift by 2 rho or delta, because that's this gap. Okay? One is rho below, one is rho above, so the gap is 2 rho times delta t. Is that clear? Okay. So now if you want to limit the max drift to some valued delta, okay, which is the small delta, let's say you say I want to limit the amount by which they're off to 1 second. So in this case, delta is 1 second. Okay. What that means is you have to resynchronize the clock every delta over 2 rho seconds. Okay, because every 2 rho seconds, you will essentially drift by that much amount. So you will essentially want to run the resynchronization algorithm every so often. Means every so often, which is delta over 2 rho seconds, you want to make sure the two clocks are now resynchronized, so that again they are telling the same time. And then they'll drift, and after another delta or 2 rho, you resynchronize them, then they are synchronized again, and so on. Okay? So every clock synchronization algorithm involves figuring out for that clock what is the drift rate. Okay? Some user has to specify this delta, saying that you want to make sure that the clock is not going to be off by more than delta. You can mention any value, 0.1 second, 1 millisecond, whatever it is, right? And then that will tell you how frequently you need to run the synchronization. Right? The synchronization will essentially attempt to then resynchronize that clock. Is this clear? Okay. All right. So this is just very basic stuff, but now we'll talk about an actual clock synchronization algorithm that's going to use that idea that I just mentioned. Okay? So in this case, this is called Christian's algorithm. It's named after the person who came up with this. Okay? We essentially assume that there is a time server. So now we are talking about computers resynchronizing, not you taking your watch and trying to synchronize something. Right? So there's a laptop or a desktop that needs to resynchronize itself every so often. So the way it's going to work is there's going to be a time server machine in the system. Okay? So this time server is the one that is keeping track of real time. In some sense, the time server is drawing its time from an atomic clock. Okay? And you can do this by attaching a satellite receiver to the machine, where it's listening to satellite broadcasts and synchronizing time. So we'll assume the time server actually is correct, okay, because it's synchronized with an atomic clock. Okay? And there are hardware ways to do this, but we'll not go into how the time server itself is synchronized. But what we will now do is, given a time server, a machine that's acting as a time server, how can other machines in that network synchronize with it? Okay. So the idea is very simple. Each machine has this delta parameter that says what's the error tolerance. So the machine, okay, every delta over 2 rho seconds is simply going to send a message to the time server saying what time is it. Okay? The time server will send back the time, and you will use that time to synchronize your clock. Okay? So essentially, every delta over 2 rho seconds, you are going to ask the time server for time, and then you are going to get back a response and synchronize. Okay? But as you can imagine from this picture, it's not as simple as what I said. Okay? So in this case, the y-axis going downward is time. Okay? There's one line here to the right is your time server. The other line is the machine P, or the process P. Okay? So at the top, you send a request saying what time is it, because requests are not going to instantaneously reach the time server. It takes some small amount of time for the request to reach that time server. Okay? And then it's going to be processed by the time server. The time server processes that time t, and is going to return t back to the machine. Okay? That return response is also going to take a little bit of time to reach the machine, okay, which is shown as t reply. Okay, the time the forward propagation request took time t request, the reply took t reply over the network to come back. Okay? Now, if the machine simply took t, okay, and then changed its clock value to t, you're already off by t reply, okay, because it took some time for that message to come. Time is still ticking, so but t is no longer actually the correct time at this point when the reply message was received. Okay? In fact, the correct time is t plus t reply. Okay? But the machine does not know how long network messages have taken. Okay? So somehow the clock synchronization algorithm simply cannot take t that came from the time server and change that local time to t. Then you already know there is an error. You have to estimate how long it took for the reply to propagate over the network. What is the network delay for the response to come from the server to this machine? Estimate that, and you have to actually set the time to t plus t reply. Okay? So the real question is, how are we going to estimate t reply? Okay? Once you estimate that, then clock synchronization is straightforward. Every delta or t row, you ask the time server, it sends the time, you find the network propagation delay, you add it to the time that was sent back to you, you set your clock to that value, and you're done. Is this clear? Okay, so question, how are we going to estimate this? Okay, so suggestion is, let's set a timer on the machine and wait for the response to come by. So what you can do is, when you send the request, you start a timer. Okay, the request went there, and then the response came back, and that you know have a response, the timer ends. So now what you have found is t request plus t reply. That's the total round trip time that you found with the timer. Okay, that's not exactly t reply, but you found a round trip time. Okay? So one simplifying assumption you can make is that it takes the same amount of time for the message to go from the machine to the server that it takes to come back. Okay? If you do this, you are going to take t request plus t reply. Okay? You then halve it, and you say that is my estimate of t reply. Because if it's same time, then you know the total time, round trip time. You say the one-way propagation latency is half of the round trip time, and then you got an estimate of t reply. Okay? So this is a simple example where you can take time t. You can take this estimate of t request plus t reply over 2. You take this, you add it to t, and then that's what you set here. Okay? That's Christian's algorithm. Okay? But as you can already see in this picture, okay, this was just an approximation. There's no requirement that the forward latency and the reverse latency be accurate. Okay? In fact, you see that here the t request is a little bit longer than t reply. They're just saying that the forward path may be more congested than the reverse path. Your question is?
Approximate what T request is by taking time to set request, time set back up server, back to T request, originally time synchronized, that at the time stamp request, time synchronized.
Okay. Question is, can you take T request and then subtract the time that was sent back to you? That's your question, right? If you want to do something like that, you have to assume that the process P, machine P is already synchronized with the time set, because now you are comparing time across two machines. You already assume that you are off by some amount, which could be as much as delta. Right? You don't know what the actual amount by which you're off is. That's the maximum amount. So if you take this time and you then compare it with some time here, that's going to be off. Okay? But we'll assume that T request plus T reply is the same timestamp, right? So this is fine, because the clock is not going to be, even if your clock is off, you are just taking the difference between two timestamps, that's still okay. Right? So that's fine. But if you did what the suggestion you made was to take T request and then add it to somehow T and find some estimate, that might be less accurate because the clock is not synchronized with the time server. Okay? Yes, question. Okay, question is, if the request to not request, the frequency to make the request to the time server is based on the drift rate, and the drift rate is not, can we not use the drift rate to correct for the time? That's your question, right? Yeah. So what's the problem with this? Yes. Somebody else. Yes, you have.
The drift rate's not like it's, you know, like this is about how much it actually drifts less.
So that first of all, the drift rate is just the max value. It's saying that if you buy, let's say, a Rolex watch, it's going to drift 1 second a year because that's what the company guarantees you. That doesn't mean every Rolex watch will exactly drift by 1 second. That's the maximum amount they're telling you, right? It might be drifting half a second or third of a second or 0.9 seconds. You don't actually know. It's just the maximum tolerance. Okay? Furthermore, the drift rate is also not constant because first of all, even if it was constant, it's not delta. It's not rho. It's somewhere between 1 plus rho and 1 minus rho. You don't know what it is. But secondly, it's not even constant because for most mechanical clock, the drift rate changes based on things like temperature, right? Like quartz clocks, they are using a quartz oscillator. Okay, the property of quartz crystals is actually somewhat temperature dependent. So if you go to very hot climate or cold climate, the drift will still be within rho, but it may be off from where you started. So it will not be constant, neither is it no. So you can't actually use that to correct. All you know is this is the maximum amount by which you will drift. So if you resynchronize every so often, you will be fine. You will be within delta. Okay.
Positive or negative, like how much does it? Because they are telling so not this describe it.
So your question is, how do you know whether it's positive or negative, or why is it positive? I don't understand the code. What do you mean by why is it? Yes.
Yes or more than the.
Yeah. So the drift rate is basically saying you can drift in either direction by rho. That's the definition of drift rate. It's like plus or minus. So they don't tell you that the clock can be fast or slow. They just say it will go off. It may be faster than real time or slower. So that's what the definition is. It means that it's not that it's rho. It can be rho in either direction is what it means, which is why you are here. Okay. All right. Okay. So this Christian's algorithm, okay, you can use one value of T request plus T reply over 2 and use that as the estimate of T reply. Newer algorithms will make a sequence of these requests, find a sequence of these estimates because the network conditions might change and use some sort of a mean value or multiple measurements. So you can improve the network estimate of latency, one-way latency, by making multiple measurements and so on. But by and large, all clock algorithms are going to be doing exactly this. They're going to send a request to the time server, get back a reply, but they have to correct for the network latency. Okay? So you have to estimate the network latency somehow and add it to T, and then you synchronize your clock. And this is delta or 2 rho is going to tell you, okay, that's a configurable parameter delta. It will tell you how frequently to run this program. Okay. All right. That's Christian's algorithm. So we'll talk about another one, which is called the Berkeley algorithm. Okay, and then we'll talk about several others, but these two by and large give you the basics of how most of them work. Okay, so Berkeley algorithm is an algorithm that does not use a time server. It's a relative clock synchronization algorithm. A group of machines, none of which are actually synchronized with real time, just want their relative clocks to be synchronized with one another. Okay? Nothing is actually synchronized with real time. Okay? The question is, how can n machines just synchronize their clock with one another? Okay? And they might go off with respect to real time because none of these clocks are actually synchronized. If they're all running 5 minutes fast, they will all drift at that rate, but they'll all be synchronized with one another. At least their clock values you can compare by synchronizing them. Okay? So we will not have a time server, but we'll still have a coordinator. Okay? Does not have any real, not synchronized with the atomic clock, but that's the one that runs the algorithm. So there's a coordinator, that's a worker. Okay? Very simply, the coordinator is going to send requests to the workers for the time. They'll return the time. It will compute the mean time in the system and it will send it back. Okay? And I'm going to tell you how that works. So there is a picture that explains this. Okay? There are 3 machines here, okay? A, B, and C. The top one is the time master, okay? And the other 2 are just participants, worker nodes. You will see that when you start this one has clock of 3 p.m. This one is 10 minutes behind. It's 2:50. That's 3:25. Okay? So it's going to every delta or 2 rho run this algorithm. Okay? In this case, it's basically saying what time is it. Okay? The picture actually says it sends a request saying my time is 3. Tell me the drift from my time. But you could just ask all the machines, send me your time. It's the same thing. Okay? So So in this case, you get back -10, which says my time is 250. This one says +25, saying my time is 325. And then this machine is just going to take the mean of the 3 clocks. Okay? And then send back the value saying the mean time in the system is 305. So it will send a request to this machine to advance its clock by 15 minutes. And this machine will actually bring its clock behind by 20 minutes. So now they're all synchronized and at 305. Okay? Now, everything I said in the previous algorithm for compensating for network delays still the same. That picture doesn't show it. Okay? But you still have to look at the network round trip time and then correct the clock values that are reported. And when you send it back, you have to do the same thing. Okay? So that problem has not gone away. Okay? But we said we know how to deal with that. So we are just looking at the rest of it. Okay? So this one is just tracking the average time in the system and then making sure all the clocks are synchronized. Is this clear? Okay. So that's called Berkeley algorithm. The thing you want to keep in mind is none of these clocks are actually synchronized with an atomic clock. So they may all start drifting over time, okay? But they are all synchronized relative to one another, which in some systems is all you want. If you want to compare timestamps across machines, okay, you just need the clocks to be synchronized, even though they may not be accurate in terms of real time. Okay, so there's a relative clock synchronization. Okay. All right. So there are many other approaches that you can think about. So there are decentralized algorithms that try to do this, similar to the Berkeley algorithm. There is actually on most machines, at least Unix machine, Linux and Mac, they have an rdate command that essentially does what Berkeley algorithm do. You can say rdate and give a machine name. It just talks to the machine, and the 2 clocks are basically going to get synchronized with one another. But the most common technique that is used for clock synchronization in computing systems is called network time protocol, or NTP. Okay? This is a protocol that is built into all of these operating systems like Mac, Windows, Linux, as well as all these phone-based operating systems. They all use NTP. Okay? You need an NTP server. Okay? Just as you have a time server in Christian's algorithm, it's basically a very fancy version of Christian's algorithm. Okay? So you need a time server. That time server has to be configured. Okay? If you actually go into your Windows or Mac settings and you look under time, and if you have a box that says set the time automatically, there'll be a NTP server in there. Okay? The default one on Mac, for example, is time.apple.com. That's the Apple provides the NTP server. But you can change that. I mean, UMass runs one for ntp.umass.edu. You can change it, then your machine will start using the UMass NTP server. But by and large, there's an NTP server somewhere. That's your time server. You're synchronizing. You have to deal with the same problems of estimating network latency and so on. Okay? So it's basically based on Christian's algorithm. It uses 8 pairs of measurements to get accurate estimates of network latency. Okay, Christian's algorithm, I showed you one. It uses 8 pairs, and it has things that uses what are hierarchies, where you might have other time servers that are designed based on, not designed, but devised using a NTP server and so on. So you can do hierarchical clock synchronization. So you can have your laptop in your home synchronized with the NTP server, and your laptop can provide NTP service to other machines on your home network, so they don't have to go to NTP server. So it can be hierarchical. Okay? And it guarantees that even when there is hierarchical synchronization, the maximum drift rate is limited. Okay? So NTP keeps it under, I think, 50 milliseconds. Okay? So accuracies that are guaranteed by NTP is 1 to 50. Okay? So it can be within 1 to 50 milliseconds if you use the NTP protocol. It's another way of saying the network latency estimation can be off by as much as 50 milliseconds. Okay? The clock value is correct because it's synchronized with an atomic clock, but network latency estimates can go up. Okay? Typically, it's on the lower end of that, not as high as 50 milliseconds, but that's what the protocol specifies. Okay? But there's one other thing that it does. So this is the same technique I was showing you earlier. You send a request to NTP server. Okay? So that's the forward path to get back a reply. You really want to take the estimate of just this part, but you're going to take the whole thing and assume that both paths are symmetric and so on. And you do that 8 times to get good measure. Okay? Yes.
Just set the time with the work we want to do. The machine can just do the work according to the.
Okay. Question is, why do we need to synchronize time with other machine? That's your question, right? Yeah. So typically your laptop will tell you time, right? I mean, if you have, yeah, right. So you have time there, right? So if you are looking at the time, that time better be accurate, right? It's not that your only programs are using time. Every computer is telling you a time because it is a clock. You want that clock to be accurate, right? So that to do that, you need to synchronize that clock. It's not that you just have a program that needs the time. It's just the time. Your phone has a clock on it, right? You as a user use it. Of course, programs use it too. If that clock is off, it won't tell you the correct time. So all of these computing systems are using NTP to actually set the clock. Okay? So it's not just for programs. It's just you want that clock to be accurate for any number of reasons. Any other questions? Okay. Yes. Yeah.
Each of them can have their own drift. So when exactly?
Okay. The question is, in the Berkeley algorithm, if each clock has its own drift rate, how frequently should we use that? That's a design choice. You can, there are many assumptions. If you have homogeneous machines, the chips will be identical. They'll all have the same drift rate. But that's not going to be true in general. You might have Windows laptops, Linux laptops, different manufacturers. So they will have different chips, different drift rate. So what you can do is take the min drift rate across, not min, the max drift rate across all of the chips, and then use that to synchronize it, because if the worst case clock is accurate, then all other clocks are right. So if you have different drift rates, you should just take the max of the clocks and use that to synchronize in the Berkeley case. Okay. All right. So that's a good question. But the other thing I did want to mention for NTP is there's one additional difference that I didn't talk about for Christian's and Berkeley algorithm, is that your clock in NTP cannot go backwards. Okay. So if your actual clock is running fast, okay, and then the Christian's algorithm can say move it back by 5 minutes. Berkeley algorithm, you saw an example where we actually moved this clock back 20 minutes, right? And NTP, the assumption is that clocks can move forward, okay, but you are never going to move a clock backwards. Okay? The first question is why would we not want to move a clock backwards? Yes.
Because some things might depend on correct times.
Some things might depend on correct times, and somebody else said something. Yes.
Yeah, some programs might not like it. Have all of a sudden the technology messed up. Some things now look like they're in the future or in the past.
Okay. Yeah. So think about what might happen if clock is actually moved backwards, right? The first thing is you have, let's say you have a timestamp on a file. You modified a file, okay? So it has a timestamp, and you move the clock back. Now that time is actually in the future. It hasn't even occurred. So that's not a thing. Okay. And second of all, you might have two things with the same timestamp, but that they actually occurred at different times, but you moved the clock back, right? So we have noon, you timestamp something, you move the clock back by 10 minutes. There's another noon, you timestamp it. You will assume that both of those things actually were modified at the same time, but they were actually modified maybe minutes apart. Okay? So when you move a clock backwards, all bad things happen. There's the timestamp in the future. There may be multiple timestamps that are identical, but they're in fact not identical. So you don't want to do that. Okay? Moving a clock forward, there is no problem, because you're just jumping time. You will never have a case where you have two timestamps that are identical, but they're actually two different times, because you're just skipping. In this case, not when you move back, you're repeating some times that have already been occurred on that clock, right? So you don't want to do that. Okay? So then the question is, if clock cannot go backwards, how will you synchronize in this case, right? Because you still want to synchronize the clock. You're just not allowed to move it back. The way you will do it is you will slow it down. Okay? Instead of moving the clock back, you'll slow down how frequently you tick the clock and have real-time catch up with the clock, and then you continue. Right? So that's what NTP will do. It will actually slow down the rate at which the clock ticks, or you will say every time the clock ticks by 2, I'm going to assume real-time only advanced, not real-time. My clock advanced by 1, so I've slowed down by half, and I'll wait for real-time to catch up, then I'll just continue. Okay? That's how you are going to make sure that you will not have the clock go back. Okay? So that's a restriction in NTP that's important to keep in mind. Yes, question. Okay. Question is, what does slowing down mean? Are you adding a delay? So you're not quite adding a delay, but it's basically you have to think about how clocks work, right? So let's say it's a quartz crystal. Okay. So the quartz crystal says every time the crystal vibrates n times, you advance, you say it's 1 second, you tick by 1. Right? So you might say, rather than it every time it vibrates 100 times, I tick by 1. You might say, every time it vibrates 200 times, I tick by 1. So I'm actually slowed it down because I'm not advancing my software clock based on what the actual clock is telling. Right? So that's how you can slow it down. You're not adding a delay. You're just slowing the rate at which your clock is advancing on your machine. And then you wait for the actual clock to real time. Yes. So I mean, you will not. Yes. So you want to say, I want to change the clock. The clock has to go back by 1 minute. Let's just take an example. So I can essentially slow it down such that in 30 seconds I catch up. So I will calculate it for how long you slow it down, and then you reset. Right. So you have to do all of that. Okay. So as you can see, it has more sophisticated features in terms of network measurement, the fact that you can have hierarchies, but most importantly, not moving clocks back, with the other two techniques that we talked about did not do. Okay. Is that clear? Okay. All right. So next thing we are going to talk about is global positioning systems, or GPS. Okay. I'm assuming you're all familiar with GPS. If you used a map to give you directions, you're using GPS chip on your phone, or whatever your GPS device is telling you how to do directions. But what we'll see is, what does the GPS do, and what does that have to do with clock synchronization? Okay. Because the goal here is not to learn about GPS, it's to learn about clock synchronization. But we will see how to solve the clock synchronization problem using GPS. Okay. So first thing is, I have to show some basic techniques about how GPS works, and then we'll see why we can, not why, but how we can solve clock synchronization algorithm. Okay. So what does GPS do? Okay. GPS basically is a technology where there are a set of satellites, okay, that's already been launched. Those satellites have a known position in space. So they are essentially geostationary satellites, so they're at a known location. Okay. So the location of these satellites in the sky is known, okay, and they are precisely positioned at that location. Okay. Furthermore, in GPS, these satellites have clocks that are synchronized with an atomic clock. Right. So each of the satellite is just broadcasting time. Okay. So there are satellites in space, there are known locations, okay, and they are essentially broadcasting time. Okay. So a GPS receiver is simply a chip on any computing system or a phone that's just listening to satellite broadcast. Okay. And for each broadcast that it receives, it also knows which satellite sent that broadcast. So it knows precisely what the location of that satellite is. Okay. And the problem in GPS is the GPS receiver, which would be a chip on your phone, has to figure out its own location, okay, in some 3D space. It needs to find its own coordinates, so it knows where in the 3D space it is located just based on satellites that it's listening to. That's the GPS locationing problem. Okay. We will see how to solve this problem, but at least I hope the problem is clear. Okay. So I'm going to draw a picture here because that picture is actually not very clear. Let me show you an example. So let's say, I'll just take the picture there. Let's say the satellite is in space. It's at God. We'll just start with 2D space for a moment. Forget 3D. This is just 2D. Okay. So we'll assume that there's a satellite at this known location. Well, let's call it XY rather than this. Okay. And it's just sending the timestamp. So it'll basically say this is the time. It's just sending this network packets, and there's a receiver here, okay, that essentially gets this broadcast. Okay. So let's say this receiver sends a clock value t. Okay. And it has now received, not the receiver, rather the satellite sends clock value t. It's now received by the receiver. The receiver's location x prime, y prime is not known at the moment, but x and y are known because the satellite is at a known location in space. Okay. So now the question is, how can this receiver find out its coordinate with respect to the coordinates of the satellite? That's its location. So what do we know about this problem? Okay. First thing we will know is these broadcasts are going as a wireless broadcast. Okay. So they are going to basically propagate at speed of light. All wireless communication occurs at speed of light. Okay. So let's just for 1 second assume that the receiver sent this thing at t, okay, and it was received here at time t plus d. Okay, so d is the distance here that we don't know. Okay, and this distance basically, so this is going to propagate at speed of light. Speed of light is known. So let's say just for a second, okay, let's say it was sent, this packet was sent at t and it was received here at t prime. Okay, so essentially this distance d is t minus t prime minus t. Okay, because that's the time it took for the packet to go. Okay, that's so if you do speed is distance, distance over time, you'll say the speed of light is known. This is the time. So d is essentially speed of light time that delay. Okay, is that clear? Okay, so that's something we will use. Okay, but as far as, so if you say I'm at a distance d from this satellite, which is this, what does it tell you about your coordinates? What is the point that's at a distance d from the satellite? It's a radius, right? So it basically, the circle is, so basically all you know at this point is this receiver is on a circle which is at a distance d from the satellite. That's all we know, because we know it took d for the packet to propagate. Okay, and so now all we know is that that the receiver is somewhere on a circle. We don't know where it is because all points on the circle are equidistant from the satellite. Okay, so we have now localized this receiver to a circle, but we don't know where exactly it is. Okay? So now we can repeat this. And let's say there's a second satellite, okay, which is now at some other location. Okay, we'll call it x1, y1. Okay, and you repeat this process with that satellite. Okay, it's going to send broadcast. You'll find when the broadcasts were received. You'll take the difference in the timestamp when it was sent, the time it was received here, and then you know the speed of light, so you know the distance to that satellite d prime. Okay, and you will now localize it to a second circle. Okay, because then you are now on a second circle with that second satellite as the center of that circle. Okay, now the receiver is at a single location that has to be present on both of those circles. Right, so that's how you're going to localize. So that's what's shown here. So these two black dots are two satellites. First time you localize it to a radius that's on the first circle. You can be anywhere on this. Then you use a second satellite and you now localize this. So the receiver has to be essentially on both of the circles at the same time because it's at a given location. So it's going to be on the intersection of these two circles. So now you narrowed it down. Two circles can intersect at most 2 points, right, which are shown here. Okay, they can intersect exactly 1 point if they were actually tangential to one another. But now you are localized it to one of two locations. Okay, so now we basically, from not knowing its coordinates, we are down to 2. You just take the intersection. You could do a third one and then you will find it. Right? So that's basically how GPS is going to work. It's basically you have a receiver on the ground. It's listening to satellite broadcasts. Okay, you now do this problem in 3D, not 2D. Right? So the first time around, you'll find a location on a sphere, because sphere is all the points that are at a distance d from a satellite. Okay, then you take a second satellite and then you have another sphere. When two spheres intersect, what do we get? You get a circle. Think about two spheres. If you actually intersect them, you'll get a circle, right? So you'll get a circle. So once you have two spheres, you're down to a circle. You put a third sphere, you'll basically get two circles that intersect, and then you do that and you'll get your answer. Okay, but that's how GPS works. Okay, so far we've not talked about any clock synchronization. Okay, so we'll say, why do we need clock synchronization at all in this problem? Okay, what you will realize is I implicitly assume that the clock on this receiver is synchronized with the satellite. Otherwise, you can't do t prime minus t accurately. If this clock is off, this latency difference is going to be completely off. Okay, this will only work if these two clocks are synchronized. Okay, they have to synchronize very well if you want to actually localize that to, let's say, if you're using GPS when you're driving, you have to be within 10 feet of where your thing says, or maybe 50 feet. Otherwise, the The GPS will show you on some other road or something like that, right? So you have to be pretty accurate. So these two clocks have to be synchronized, right? We assume they were. That is why you could do the speed of light minus the difference between the time at which this packet was sent and when it was received. Okay? But the clock on that receiver is not synchronized. That's an assumption we made, right? So now what do we do? Okay, so you are saying we will use some clock synchronization algorithm. Okay, but all messages are only going one way. You are not, GPS receivers do not send a request to the satellite. If you did that, you could use Christian's algorithm. Okay, GPS receivers are one way. So you don't have the luxury of doing what we did so far, where you send a request, what time is it to the satellite, it sends a reply, then it would be fine. But that's not what we are doing. Okay, you are only listening. You cannot communicate with the satellite. You can listen to satellite. Okay? We'll use simple geometry to solve it, because what we'll assume is the clock on this is gone off by some amount delta, which we don't know. Okay? So T prime is actually some T plus delta or something, or let's say it's off by delta. Okay? So we have to correct for that drift as part of GPS. Okay? So we'll build in the clock synchronization into GPS, so this problem doesn't even arise in the first place. So we'll drop the assumption that the receiver's clock is synchronized to begin with. We'll assume that it's off by some unknown amount delta. Okay? So now we have not, so earlier there were three unknowns, which is x prime, y prime, z prime, which is the coordinates of the receiver. Now there are four unknowns, the three coordinates of the receiver and the clock drift delta. Okay? Now the question is, how are we going to find this? Yes, you can add more satellites, you can do that, but that still doesn't tell you what delta is. We will have more satellites, but we need one more fact to actually solve this problem. So we'll use a second well-known fact. I mean, one thing was we said speed of light is known, so you will have distance d is essentially speed of light minus this difference. But we'll use another fact that we know, which is Euclidean geometry. Okay? What is the distance between 2 points? Okay? So as you probably know, that's the formula there, which I'm going to write here. Distance between any 2 points is essentially d is going to be x minus whatever we said here, x prime square plus y minus y prime square plus z minus z prime square. Okay? X, y, and z are known. X prime, y prime, z prime unknowns. Okay? So that's one equation for d. But we have a second equation for d, which is this: is d is now c times t prime plus delta minus t. Right? In this case, delta is unknown. Previously, we assumed it was known, but now we don't know this delta. Okay? These two equations are the same, give you the same d. So we are essentially going to now say this. Okay? That's an equation. So nonlinear equation, but it's still an equation with four unknowns. Okay? X prime, y prime, z prime, and delta are not known. Okay? You are now going to repeat this with multiple satellites. Okay? If this is a linear equation, 4 satellites will do it. 4 unknowns, 4 linear equation. But this is not a linear equation, it's a non-linear equation. So you might need 6 or 7 satellites, and essentially you use those equations to solve for 4 unknowns. Okay? Typically you will need minimum of 4, which is why it says 4 means you at least need 4. Without 4, you can't do it, but this is not linear, so 4 will not actually give you accurate results. So you have to find at least more than 4, maybe 6 or 7. You will get 7 of these equations. Okay? And then you solve for 4 unknowns using non-linear technique to solve these equations. Okay? And then if you do that, you not only got x prime, y prime, z prime, but you also got the delta by which the clock was off. So you can synchronize the clock as well as part of this. Okay? And even if you don't synchronize the clock, at least you know your location accurately. Is that clear? So we've done clock synchronization, and we found did positioning, which is you found unknown coordinates of a receiver using GPS. Your question there is. Okay, question: is there no drift time from the satellite? We will assume, of course, satellite will have drift time, but we'll assume the satellite has already been synchronized with an atomic clock. So we will assume the satellite time is correct. Okay? Yes, if the satellite time is off, we have another problem, but we'll assume all the satellites are actually have either a built-in or are somehow synchronized with an atomic clock. Yes.
Okay, we have some multiple satellites. While blocking the device that you're using.
Okay, question is, could we synchronize the clock on the device before we do this request? That depends on the type of your GPS receiver. If it's the GPS receiver is in a phone, the phone can run an auxiliary clock synchronization algorithm to synchronize itself, then you may not need to do this. But GPS doesn't assume that the GPS chip is embedded in a computing device. Right? It's just a chip that's just listening to satellites and it's just doing onboard calculation for those equations and telling you what to do. Okay? So GPS by itself does not require you to rely on a second clock synchronization algorithm. It can solve it as part of the problem because there are already dozens of satellites that are doing this. Why not listen to 2 more and you solve the problem? I don't need a second clock synchronization algorithm in the process, right? Yes.
Delta not be constant observation.
Yeah, question is, would delta not be constant and every time you do an observation, drift changes? That is indeed correct. So this, you will have to solve this every time. Your GPS will run in a loop, right? So let's say you are in a car. Just because I found a location, a second later you're driving on the freeway at 60 miles an hour or whatever the speed is going to change frequently. So you have to run this algorithm very frequently. Okay? And as a result, you keep computing delta every time you do it because it will keep changing, right, as you pointed out. So you don't assume it's constant, you do it every time. Okay, is that clear? All right. So that is clock synchronization with GPS. Right. So we talked about Christian's algorithm, was the basic one. Then we said Berkeley one, that's relative. Then we said NTP, more sophisticated version of Christian's algorithm. We ended with GPS that says, okay, we can now solve synchronization as part of locationing or positioning. So we can find locations of a receiver and figure out the time by which its clock is off in one shot. Okay, so that is GPS. There are many other techniques which I will not talk about. There are all kinds of things you do in wireless systems and sensor networks where you synchronize with a time server. I won't go into them because by and large, they're either going to be a derivative of Christian's algorithm or they're going to be a derivative of Berkeley algorithm, one or the two. Okay? If they're sophisticated, they don't have to do either. They can actually download the NTP package and use NTP. Okay? But if you don't have the luxury of having an NTP server, you have to use one of these two techniques to do it. Okay? But what I will talk about in the next 15-20 minutes is a different approach for thinking about clocks, where we will not use physical clocks to do reasoning about timestamps. We'll use what are called logical clocks. Okay? And the reason, one of the reasons we'll talk about logical clocks is actually twofold. In many cases, you just want to compare timestamps to figure out which event occurred before which other event, right? So you might want to, in the make example, the build example, all we wanted to know was, has the source file changed after the previous build? Okay? You didn't care about did it change 5 minutes later, 10 minutes later, that part is irrelevant. We just want to know, is the source file newer or older? Right? Relative, okay? Not the absolute value. That did not matter because so long as change, you will have to recompile. Okay? So in many cases like this, you are comparing timestamp to figure out order of event, not the actual time difference between events. Right? If you want to find actual time difference between events, you have to use real clocks. Right? In your lab 1 example, you needed to find latency of your request. Okay? That requires physical clock because you want to figure out how long it took. Okay? If you don't want to figure out how long it took, you just want to say which of these occurred earlier. That's all you care about. Then you don't need physical clock. You can get away with what are called logical clocks. Yeah. The other reasons logical clocks are interesting and useful is clock synchronization is not going to be always accurate. Every clock synchronization algorithm has a built-in error. Okay? That was the error of that network latency calculation that you made and so on. Okay? So it's always going to be off. Okay? if let's say NTP is off by 1 millisecond, that's its lowest amount of error tolerance. If your two events now that are 0.5 milliseconds apart, okay, and you are using NTP, you actually cannot say which one occurred before the other, because NTP can give you 1 millisecond error. So if you have two timestamps that are inside the error tolerance, there you cannot actually say. You can just say, because this timestamp is lower, I'm assuming this event occurred before, but that's not a guarantee. Right? So no matter how accurate you make the clock synchronization, there will always be an error tolerance epsilon. If two timestamps are actually within epsilon of each other, you actually cannot say which one occurred before the other because of the inaccuracy of clock synchronization. So logical clocks are going to get rid of that problem. They don't actually rely on physical clock, so they don't actually suffer from the problem that all clock synchronization algorithms actually have to deal with. Okay? Now, as I said, when you use this concept of logical clocks, you are only trying to figure out order of events, not the time at which they occurred or the latency between them and so on. Okay? If you just want to know which one occurred before which one, but you don't care that 5 minutes apart, 1 second apart, or anything like that, you will use this concept of a logical clock. Okay? So let's now try to ask, what is this logical clock and how do we work with it? To do that, I'm going to introduce this concept of event ordering. Okay? So essentially, and then we'll construct an algorithm, very simple algorithm that allows us to get event ordering. Okay? So what is an event ordering? So let's say you have a distributed system, okay, machines that are participating in a distributed system. We'll assume that we don't actually worry about the clocks on them. We are not going to synchronize them. Okay? Instead, we will essentially say these are events we care about. Okay? It could be I sent a message, or essentially I received some message, or something else happened on the machine. There are some events that are important to this application. Okay? And you want to construct an ordering of these events across machines that allows us to figure out which event occurred before which other event, which is a total order. Okay? So given a set of events, we just want to construct a total order, and these events are occurring across machine. It's a little bit abstract because we don't really care in the algorithm what the events are. You can define any event that you care about for your application, and logical clocks will construct an order for you. Okay? So that's what the problem is. So the assumptions we'll make are the following. Okay? On a single machine, okay, we will assume that we know the order of events, because we'll assume that processes are executing instructions sequentially. Okay? Because of sequential execution of instruction, let's say your program, okay, if some events here are essentially, we'll assume they're instructions. So if there's an instruction A that executed before instruction B, okay, we will assume that whatever event is associated with instruction A happened before B, because that's the order of execution. Okay? Order of execution gives you an order that you can use to compare. Right? So for example, you might say, like simple example, right? You put a print statement, and then in your program there's a second print statement. There's no threading or anything. Sequential execution. Okay? The first print statement will always execute before the second. So you will say, if you say what's the order in which these print statements executed, you will say that one is executed for the second one, because that's execution order. Okay? So execution order on a machine gives us a natural ordering of events that are related to that process on that machine. Okay? That's one thing we'll talk about. Not talk about, we'll assume. The second assumption is, of course, we have no global clock. No global clock essentially means there's no perfect clock synchronization. Global clock essentially means perfect clock, that every machine is completely synchronized with no inaccuracy. We'll assume such a thing doesn't exist, because it doesn't. So we'll assume local clocks may be arbitrarily off. Okay? It'll be off by hours, minutes. We don't really care in this case. Okay? And we will assume that now we somehow have to figure out how to order events across machines. Okay? So that's the problem. And then we'll see how to construct this total ordering of event. Okay? The idea at the end of the day actually is very simple. And it was logical clocks are also called Lamport's clock, because they were first proposed by a very seminal paper that Leslie Lamport actually wrote, and then that gave rise to this idea. Leslie Lamport is incidentally also the person who invented LaTeX. Okay? LaTeX actually means Lamport Tech. Tech was a previous software. He came up with LaTeX. So this is the first time we have encountered Lamport, but we'll see many algorithms that he developed that are used in all kinds of distributed systems, not to mention LaTeX that we all use for writing documents and paper. Okay, but here's the basic idea. Okay? We are going to essentially use the process of message exchange to impose ordering. Okay? So, and what does that mean? If the process on machine 1 sends a message, let's say socket message, RPC message, doesn't matter what message it is, to another process on another machine. Okay? So there are two events here. There's a send event on machine A, that's the sending of the message. There's a receive event on another machine. Okay? What can we say about these two events? Okay, so think about, I'm sending a message. Okay, there's a send event and there's a receive event. Can you order them? Send has to be before receive, right? Messages cannot be received before they're sent. Laws of physics, right? So we know send and receive can be ordered. This is all we are going to assume. We'll assume that the execution on a single process can be ordered. Send and receive must be ordered. We'll take these two ideas and construct a total order. Okay? And we'll see how to do that in just one slide. Before we do that, I'm going to define this relationship called happened before relationship. Okay? So this is just a relationship that we'll use for reasoning about events. So if you say A and B are two events in the same process, okay, and A executed before B in that process, okay, I'm telling you that whatever A is related to executed first and B executed next, we know that A has happened before B because execution order is also going to be in time order. That's sequential execution. Okay? One instruction executed before the other, event associated with that event must have happened before the other. That's given. Okay? A represents the sending of a message. B represents the receipt of the message. Okay? A is the send, B is the receipt. Okay? We know A has happened before B. Okay? Message has to be sent first. Okay? Receipt always happened afterward. Okay? And there's always finite latency. Okay? It's never going to be the same time. Okay? So then we also say this relationship is transitive. Okay? If I give you any two events and I tell you A happened before B, I tell you that B happened before C, you apply transitive property and say, now I know A has happened before C. Okay? This is all we actually need to construct this total ordering, and I'm going to show you an example. Is this clear though, what I just said? We're using execution order, we're using sends and receive across processes. Now we can start ordering events. Okay? So essentially this is our algorithm. Okay? And then I'm going to show you a picture that shows you how the algorithm works. Okay? What are logical clocks? They're going to be integers maintained by processes or machines. Okay? A logical clock is simply an integer. Okay? Unlike a real clock that's going to tick with real time, logical clocks are only going to be incremented when any event you care about in your process has occurred. So let's say process has a logical clock, it will start with 0. First time an event occurs, you will increment it by 1 and give it logical clock value 1. Okay? Another event occurs in that process, you will increment that clock and give it logical clock value 2, and so on. So every time within a process any event occurs, you are going to increment the clock. Okay? Just an integer. You are going to maintain this integer. Okay? So in your process. So every machine maintains a logical clock. We call it LC1, but simply an integer. Whenever an event occurs locally within a process, you are going to increment it and give it that timestamp, which is a logical timestamp at this point. Okay? Now, when process I sends a message to process J, okay, so the process simply sending a message, socket message, RPC, whatever the message may be, you are going to always include the logical clock of the sender with the message. You're going to send this extra bit of information. Okay? You send a message, you will send the send will be an event, you will increment that, it will get a timestamp, you will include that in the message. Okay? When the receiver receives the message, okay, it's going to take the clock value that arrived in the message. Okay? It will take the local logical clock, it will compare the two, and it will take the max of the two. And the receive will essentially get the max of the 2 plus 1. Okay? So the receipt is not going to ever just be a local increment because the message has just been received with a clock on the sender. You will take the two clocks, you will take the max, and you will essentially set the receipt to be max plus 1. Is this clear what I said? I'm going to give you an example. So now if you just do this, you can get an ordering. Okay, but before I show this picture, I'm going to actually show you an example. Maybe I'll draw it on the board. It might be a little confusing. We'll get to that. Okay, so I'll draw, let's say, 3 processes, A, B, C. Each of them starts with a counter 0. That's your logical clock. Every time there is an event, you will essentially increment it. Okay, so let's say this is now up to. Okay. So you basically, when this is a send, this is a message, you send 5 with the actual message. Okay, that's the clock here. Okay, so here you're going to essentially, this would have been max of. Right, because the clock has just gone to 4 here, we'll take max of 4 and the clock that came plus 1. So this is going to get value 6. Okay, and this will continue. If this process sends a message here, same thing will happen. Okay, this is going to 7. You go here to 7. Maybe this had only incremented to 4. You'll basically do max of this and you'll basically set it to 8. Okay, that's your algorithm. That's all you're doing. Okay, just by doing this, you can use the happened before relationship to get an ordering. Okay? In particular, if I give you this event timestamp 2 on this machine A, and I give you an event timestamp 8 on machine B, okay, the event that I circled, and I say, what can you say about these 2 events? Which one has happened before which other event? Okay? You will say, the first one, the 2 has happened before, but the reason is transitive. Okay? Because these events are executing on the same machine. So you'll say 2 happened before 3, 3 happened before 4, 4 happened before 5. Okay, this send has happened before receive, because the send can never happen before the receipt. You have to send it first. Send happened before receive, then this is an event here, and 6 happened before 7, 7 happened before 8. So now you have a transitive relationship between all of the messages before the send on the sending process and all the messages after the receive automatically got ordered. Just because we said send cannot happen before the receive, we just found an ordering without using any clock synchronization, just using simple reasoning. Right? So a send of a message and a receipt of the message allow you to take all the events before the send and all the receive events after the receive and order them. Okay? So that's what this algorithm will allow you to do. Now you could take, let's say, the 2 here on machine A and 3 on machine B, and so what can you say about these 2 events? Okay, so what you have to see is these are events across machines. So you can't just look at the timestamp and say 3 is greater than 2, so that gives me an ordering. That's not actually the case. You have to see, is there any message exchange between these 2 processes that allow us to order these 2? In this case, there isn't one, right? So these 2 messages cannot be ordered. So it's going to, this technique, in other words, is only giving us a partial ordering. The partial ordering are precisely the events before the send on the sending machine and after the receive. Okay? We cannot say anything about what happened after the send here versus what happened after the receive there. Those are not ordered, or these. So not every event gets ordered, but over time there'll be lots of messages going back and forth. So lots of events will get ordered, but not all of them. So it's a partial ordering. But we got this partial ordering simply using this algorithm. Okay, yes, question. Okay, question is, if it's an integer, we will hit upper limit, what will happen to this clock? So there are 2 answers. The abstract case, it's an integer that can go to infinity, right? So in the abstract, algorithm is not impacted, but an implementation of it, of course, if it's a 32-bit integer, you can only order 2 to the power 32 events. After that, the clock will actually reset back to 0. Then you cannot do it. So either you have to assume that the size of the integer you pick for this clock is larger than the lifetime of the processes and the number of events you hope to process. Okay? So you can pick for 64-bit integer, you can pick 128-bit, whatever it is, you got to pick the length of that integer to be greater than the number of events, so that you do not actually have a wraparound. Okay? But yeah, in implementation, that's an actual problem. The abstract case, these are just integers, they keep incrementing. Okay? So in any case, here is an example of what is shown. These are processes, these are logical clocks. In the first case, you will see that you are actually not making any adjustments here. In particular, if you look at M3, you'll see the sender has timestamp 60, the receiver has timestamp 56. If we didn't do anything, okay, we are not respecting the property that the receipt has happened after the send because the timestamp here is lower. Okay? And you will see here that if you use that technique, what I just said, you will take the max of 60 and 56 plus 1 and you'll set this to 61. So this means that that send and this receipt are now ordered. So all of the events in the P3 before the send and all the events after the receipt on P2 get ordered based on this property. Okay? Same is true of this message M4 that went from 69. It goes here, it was still 54. You sent it to 70. So that also gets the order. So you will always have to do the max of the 2 clocks plus 1 to ensure that the property of happened before is satisfied. Okay? All right. So we have a nice idea, which is we are simply using integer values. We are incrementing them when events occur, and we are simply using basic ideas of sequential execution and send and receive property to order events. So it's a nice idea. But what it has actually given us is a property that only goes in one direction, not in the other. Okay? What that means is if you know that these two events are actually happened in a certain order, you will see that the timestamp respect that ordering. Okay? But the reverse is not true. If I give you two arbitrary timestamps and say, can you tell me something about the ordering? Just by looking at the timestamps, you cannot reason about them. Okay? For the same reason here, the event 2 in A and 3 in 2, they have an ordering numerically. Okay? But if you look at that picture, there's no actual ordering based on the happened before relationship because there was no message exchange to tell us that. Right? So even in this case, if I just give you two integers here, let's say I give you 14 P2 and 36 here, you can't just compare these two timestamps and so that event has occurred later. That's not something you can do with Lamport's clock because the relationship only goes one way. If two events have happened in a certain order, the timestamping algorithm gives them timestamp that respects that order. Okay? If A happened before B, okay, the timestamp of A is always going to be, so if A happened before B, then the clock value of A or the timestamp is less than time. That is what we have ensured. The reverse is not something we have done. Okay? What you really want is the implication to go both ways. You want if A happened before B, whatever timestamps you have put actually respect that ordering. The one that is A has to have a lower timestamp. But I should also be able to compare these two timestamps and say this timestamp is lower. So I should make sure that that event has actually happened before. Okay? Lamport's clock don't do that. But in the next class, we'll talk about a generalization of Lamport's clock that will give us properties that go both ways. So then you can compare timestamps and also respect happened before relation. Okay? So we'll talk about that on Wednesday. Okay, let's stop here for the day.